Astrology has been practiced for thousands of years. Homeopathy has millions of devoted followers. Intelligent design claims to offer an alternative to evolution. But are any of these science? And more fundamentally, how do we tell the difference between science and everything else? This is the demarcation problem, one of the central challenges in the philosophy of science. It asks, what distinguishes genuine science from pseudoscience, metaphysics, or mere opinion? The answer matters enormously. We fund science, teach it in schools, and use it to shape policy and medicine. If we can't say what science is, how do we know what to trust? The most famous answer comes from Karl Popper, who proposed what he called the criterion of falsifiability. Popper noticed that theories like Freudian psychoanalysis and Marxism seemed to explain everything. Whatever happened, the theory could accommodate it. A failed prediction? That was just a special case. An exception, a reaction formation. But this flexibility, Popper argued, was a weakness, not a strength. A genuinely scientific theory must be falsifiable. It must make predictions that could, in principle, turn out to be wrong. Einstein's general relativity predicted that light bends around massive objects. That was testable. When Eddington's 1919 eclipse expedition confirmed it, Einstein became famous. But crucially, if the light had not bent, the theory would have been falsified. A theory that can't be wrong can't really be right, either. Popper's criterion is elegant, but it faces serious objections. The first is the Duhem-Quine problem. When a prediction fails, it's never just the core theory that's being tested. It's the entire web of assumptions, instruments, and auxiliary hypotheses. Scientists can always save a theory by blaming a faulty assumption elsewhere. When Newtonian mechanics predicted the wrong orbit for Uranus, astronomers didn't abandon Newton. They postulated an unknown planet. And they were right. They found Neptune. The second problem, historical science, Darwinian evolution, geology, cosmology. These sciences reconstruct the past from present evidence. They make predictions about what fossils we'll find, what rock layers will look like. But the core claims that dinosaurs existed, that the universe began in a hot, dense state, aren't directly falsifiable in Popper's strict sense. Does that make them pseudoscience? Almost no philosopher of science thinks so. Thomas Kuhn offered a radically different picture in his 1962 masterpiece, The Structure of Scientific Revolutions. For Kuhn, science doesn't progress by testing and eliminating false theories. It works within paradigms, shared frameworks of assumptions, methods, and exemplary achievements that define what counts as a good question and a good answer. Normal science is puzzle solving within the paradigm. Scientists don't try to falsify it, they trust it and use it. Anomalies accumulate over time, results that don't fit the paradigm. For a while, scientists explain them away or ignore them. But when anomalies become severe enough, a crisis develops. And eventually, through a process Kuhn called a scientific revolution, the old paradigm is replaced by a new one. The Copernican revolution replaced Earth-centered astronomy. The Einsteinian revolution replaced Newtonian mechanics. These were not just discoveries. They were total reorganizations of scientific thinking. Kuhn's account is illuminating, but it raises a troubling question. If scientists are working within paradigms, and paradigms shape what counts as evidence, how do we evaluate competing paradigms rationally? Kuhn seemed to suggest that paradigm shifts involve something more like conversion than rational argument, that in some sense, adherents of different paradigms inhabit different worlds. Critics worried this led straight to relativism. The idea that no scientific theory is objectively better than another, just different. Imre Lakatos tried to rescue rationality from Kuhn while still improving on Popper. His theory of scientific research programs distinguishes two parts of any scientific framework. The hard core is the central set of assumptions scientists treat as inviolable. Surrounding it is a protective belt of auxiliary hypotheses that can be modified to handle anomalies. What makes a research program scientific and progressive, Lakatos argued, is whether its modifications make novel, surprising predictions that turn out to be true. A progressive research program generates new predictions beyond what it was designed to explain. Einstein's program predicted light bending, gravitational time dilation, gravitational waves, all confirmed. A degenerative research program makes only ad hoc adjustments, modifications that explain the problem away without predicting anything new. For Lakatos, Newtonian mechanics wasn't abandoned because it was falsified. It was abandoned because the Einsteinian program was more progressive. Paul Feyerabend pushed the skepticism further. Science, he argued, has no single method. The history of science is full of scientists violating supposedly universal rules and succeeding because they did. Galileo ignored contrary evidence. Darwin theorized well beyond his data. Feyerabend concluded that the only methodological principle that doesn't hinder progress is anything goes. He wasn't saying science is worthless, but that no algorithmic method defines it. Most philosophers of science today think demarcation is real but messy. Science is probably best characterized not by a single criterion but by a cluster of features. It seeks empirical evidence, makes predictions, aims at coherence across domains, is self-correcting through peer review, and its results are reproducible. No single feature is sufficient. Pseudosciences often mimic some of these features. What distinguishes science is the overall pattern, the web of epistemic virtues working together. The demarcation problem isn't just academic. Courts have had to decide whether intelligent design counts as science. Health agencies decide which treatments to fund. Governments respond to climate change, vaccine safety, and GMO research. All of these require some sense of what makes scientific consensus trustworthy. The demarcation problem reminds us that these questions, what is evidence? What is explanation? What is scientific progress? Are never settled once and for all. They require constant philosophical vigilance. Science might be undefinable in a strict sense. There may be no single bright line separating it from everything else. But that doesn't mean anything goes. Popper was right that testability matters. Kuhn was right that science works through shared frameworks. Lakatos was right that progressive prediction marks good science. And Feyerabend was right that method alone doesn't determine success. The demarcation problem is a reminder that science is a human enterprise. Extraordinarily powerful, but requiring constant reflection on its own foundations.